Okay, so now this entropy condition becomes a guiding principle towards us actually building the numerical flux. So remember, when we are using finite volume, we are approximating the solution as using just the volume averages, right? Something like this. And then we need to construct what is the flux at a interface between two volumes. So this is the quantity we want to get. And this flux, as we have seen, is not easy to actually reconstruct. And the most trivial ways to do it seems to all give us troubles. Right? Either they don't work well in discontinuities, if you're using central average, or they would give us a correct discontinuity, but would actually also give us incorrect discontinuities. So what's the best way to reconstruct the flux? Let me just give you two cases, right? So the first case is actually, the two cases exactly coincides with what we just had. In the first case, we had the left cell Wi equal to 1, and Wi plus 1 equal to minus 1. And the second case is the opposite. Well, do it over here. The second case is Wi equal to minus 1 and Wi plus 1 equal to 1. So the question is, in the first case, what should Fi plus half be? And in the second case, what should Fi plus half be? First of all, let's answer the first question. In the left-hand side case, what should I plus half be?
Should be 0.
Should be 0. Why?
Or rather, half.
Yeah, so we have the same person giving two competing answers, 0 or half. So anybody has a third answer here? Depends on what?
Which direction the wave is moving?
That's correct. But in this case, which direction is the discontinuity moving? It's stationary, right? Okay, the discontinuity is going to be there. It's going to be stationary. Okay, so good point. If you use the upwind scheme, so which actually we showed to be working for this case, right? If you use the upwinding scheme, what F should you get? 1/2, right? Okay, so the 1/2 if we use upwinding scheme. Okay, so anybody who vote for 0? Well, okay. If you use the central scheme, by averaging the fluxes, what would you get? Also 1/2, right? The only place you would get 0 is if you use the central average for U and then take the flux, you would get 0, which we have shown to give us extremely oscillatory solutions, right, for this case. Well, so the correct answer is actually half over here, right? So as another argument for the flux being a half is that in this case, the discontinuity is maintained, it's stationary, it doesn't change, right? Discontinuity is going to be discontinuity forever if the left-hand side is always equal to 1, right-hand side is always equal to minus 1. So if that's the case, then all the fluxes, the difference of flux across any volume, right? So basically look at this. It should be 0 for the solution to maintain fixed. So if the derivative of the integral of W has to be 0 for across any domain, then the flux should cancel out anywhere. Which means the flux, I mean, we already know the flux over either 1 or minus 1 regions are half. So the flux at the discontinuity should also be half. So this is correct. All right? Okay, case 2. what should the flux be? Should it also be half? I think the entropy condition we just discussed.
So number 1/2, it would just stay there, just like number 1 solution.
That's right. If I set Fi plus half to be half, I would get the non-entropy satisfying solution, because the flux would just cancel out with the neighboring fluxes. My solution wouldn't change, right? So what should the flux be? Oh, I mean, if you look at this solution, right, and if you discretize that using finite volumes, right, and you would say, okay, if the solution fans out like this, how should the volume average on cell I and cell I plus 1, how should they change over time? Should they decrease or increase or what? 0? Wait, so should the volume average in cell I increase or decrease? Decrease, right? So in this region is decrease. In this region is -1. In this region is +1, and in between it's gonna become smoother and smoother. Remember, if I draw the solution over here, the solution should be initially a discontinuity, right? Maybe I should draw it over here, and then it becomes like that, and then becomes like that, and becomes flatter and flatter, right? So should the cell average in a volume I increase or decrease over time? It should increase, right? And how about the volume average in cell I plus 1? Should decrease, right? So what should the flux be? I know the flux over here initially is going to be half. The flux over here initially also is going to be half, right? So what flux should happen in the middle? What should the flux be in the middle? More than a half? Oh, remember the ddt of Wi bar is equal to, I mean, if I move the term to the right hand side, then it's equal to Fi minus half minus Fi plus half, right? So Fi minus half is going to be what? Half, right? So for this to increase, Fi plus half has to be what? Huh? Yeah, good. Huh? Less than 1/2, right? So this has to be, so this is half, this has to be less than half, okay? For the Wi to increase. And you do the same math for I plus 1, you also find the same conclusion. Fi plus half has to be less than half. So yeah, less than half, but exactly what it should be. So okay, so viscosity term, that brings up a good line of thought. If you do have a viscosity term, right, then after infinitesimal amount of time, what is actually W at the interface? It becomes 0, right? Actually, if you just look at this solution, the physically correct solution, what is the value of W? Or what is the flux after infinitesimal amount of time? 0, right? So after infinitesimal amount of time, the physical solution is going to have a 0 value at the interface. Therefore, the correct flux should be 0 squared over 2. Okay? Does it make sense? No? Okay. Actually, what's the commonality between these two? I mean, am I just making up different scenarios, and in different scenario it's just a completely different line of thought, or is there any commonality? We can draw some rule that we can actually implement for any situations. What's the fundamental similarity between the flux I got in this case and the flux I got in that case? Is there any part of the argument I used for f equal to 0 on the right hand side would be the same for me to say, okay, draw conclusion f should be half in the left hand side? No idea? Actually, in both cases, the correct flux is the flux after an infinitesimal amount of time. Right? So if I'm on the left hand side is this case, right? So this is case 1. And for case 1, after infinitesimal amount of time, the discontinuity is there, it's still there, right? The flux at the discontinuity, it's still half. While for the second case, this is the second case, after infinitesimal amount of time, the discontinuity disappears and the flux over there is 0. Does it make sense?